Good afternoon everyone and welcome to today's worked exam answer video. Today I'm having a look at a transition metal question, which is one of the final year 13 topics that you will either be coming across very soon, perhaps in the next couple of weeks, or in some cases you might have already started to have a look at this before the Christmas break. So transition metal chemistry is one of the inorganic year 13 topics, and I thought I'd have a look at this today, like I say, because a lot of you will be coming onto this soon if you haven't already. So we've got 7 marks here. With any inorganic chemistry topic, they tend to be very factual, recall heavy. So you'll see that in this question because we're having to define some keywords, state a couple of factual things, and then recall some equations. So there is less understanding, or there can be less understanding with some of the inorganic chemistry, and it is more about memory, learning. So whatever works for you in terms of flashcards, having the key information stuck upon your walls, making mind maps, or kind of doing making like a Quizlet or something like that. It's obviously what works for you, but there is a lot to learn. So we are told that vanadium 5 oxide, where the 5 is representing the oxidation state of vanadium, it's used as a heterogeneous catalyst in the contact process. So we're going to need to know what a heterogeneous catalyst is, and we do need to be aware of what the contact process is, and the equations that show how the vanadium 5 oxide acts as a catalyst in that process. So for our 7 marks, explain what is meant by the terms heterogeneous and catalyst, and state in general terms how a catalyst works. So there's already kind of 3 things that we're having to do there. State the essential feature of vanadium chemistry which enables vanadium 5 oxide to function as a catalyst, and by means of equations suggest how it might be involved in the contact process. So the whole transition metal topic is all about the different properties that all of the transition metals will have, and the essential feature that they're referring to is the fact that all transition metals will have variable oxidation states, and we've known some of these examples for a very long time. For example, iron can be in the +2 oxidation state or the +3 oxidation state. In the transition metal topic, you'll have a look at a couple of other examples, including vanadium. Vanadium can exist in 4 different oxidation states: +2, +3, +4, and +5. And we can change between those oxidation states really easily. And that is what makes transition metals be very good catalysts. So for those of you who studied AQA at GCSE, you will have learned, again as a kind of comparatable fact, that transition metals are good catalysts, whereas if you've got something like sodium or magnesium, so a group 1 or 2 element, they're not very good catalysts, and that's because they have fixed oxidation states. Sodium will always be +1, magnesium will always be +2. But because vanadium can be 2, 3, 4 or 5, we can switch between those oxidation states, and that makes transition metals excellent catalysts. So those are 2 features that link together. We've known about catalysts for a very long time, probably. Lots of people have learned about them even before GCSE, I have no doubt. But here, clearly we're still going to get marks for explaining what is meant by the term catalyst and explaining how it works. So, a catalyst will speed up the rate of a chemical reaction whilst remaining chemically unchanged. Now, that can be a little bit misleading, because we can change the catalyst during the course of the reaction so long as we then regenerate it in its original state. So we're going to be changing the vanadium's oxidation state so long as we then put it back to what it is at the beginning, which is the +5, then we would say that the catalyst has remained unchanged chemically. It technically hasn't during the course of the reaction, but from the start to the finish, it looks the same there in those 2 points. So that will be our general definition of what is meant by the term catalyst. And then in general, how it works is provides an alternative reaction pathway, so a different way of reacting, and that alternative reaction pathway will have a lower activation energy. And if it's got a lower activation energy, that means that more of the particles will have energy greater than or equal to the activation energy, so we'll get more successful collisions per unit time. And it's all about the number of those successful collisions per unit time that determines the rate of a reaction. So that's the catalyst defined and explained how it works. The word heterogeneous, which is new for this topic, I can't spell, heterogeneous, refers to the state or the phase of the catalyst in relation to the reactant. So we can have homogeneous catalysis and heterogeneous catalysis. So hetero, different, homo, same. So in a heterogeneous catalysis example, the catalyst will be in a different state of matter or a different phase to the reactants. And that's what we would need to be defining here. So catalyst is in a different phase to the reactant. And in this particular example, the vanadium 5 oxide is a solid, and the contact process involves turning SO2 into SO3 for the purposes of making sulfuric acid from the SO3 that we make, so sulfur dioxide into sulfur trioxide. And they're all gases. The vanadium 5 oxide is a solid, and that's why this is an example of heterogeneous catalysis. So, next thing I need to say is the essential feature of the vanadium chemistry. So, vanadium 5 oxide can function as a catalyst because of vanadium's variable oxidation states. So those are two very heavily linked features of transition metals. Now, when it comes to, by showing via a means of equations, how it might be involved in the contact process, I've written the overall equation up there. Whenever we're showing how a catalyst gets involved in catalyzing a reaction, the catalyst itself will not appear in the overall equation because, as we've said, catalysts need to remain chemically unchanged over the course of the reaction. So if we have the V2O5 at the start and we have it at the end and it appears on both sides of our equation, we'd be cancelling it out from both sides, and that's exactly what we do need to do. So we need to make it so that the vanadium 5 oxide gets involved in the first step and changes, and then in the second step we change it back again, and all intermediates will need to cancel as well. So what we're going to change the vanadium 5 oxide into is vanadium 4 oxide. So then that intermediate will then have to cancel as we turn that back into the vanadium 5 oxide. So here is how it works. So first of all, if we're thinking about the formula of this vanadium 5 oxide, vanadium's in the +5 oxidation state and oxygen has an oxidation state of -2 in compounds. So if those are my oxidation states, in order to balance those to give me an overall formula with 0 oxidation state, I'm going to need 2 vanadiums and 5 oxygens. So that's where the V2O5 comes from, and that's a solid. And we would first of all be adding that to the SO2, and that will then give me, sorry, that's a gas. That will then give me SO3, so the vanadium 5 oxide provides an oxygen to the SO2 to make it into SO3, and then the oxidation state of vanadium therefore drops down to +4. So here each oxygen is -2, which is -8, so the 2 vanadiums need to be +8, so each of them will be +4. So I'll pop those on here as well so we can see what's going on with the oxidation states. And that's a really bad 2. Okay. Now, as I said, this V2O4 can't stick around because we have to, well, 2 reasons. We can't have intermediates in the overall equation and we have to reform the catalyst. So that's then where the oxygen comes in. And there's 2 ways we can balance this second step. We can either put a half there, or we can have 2 V2O4 plus O2. I'm going to go for the half because it makes life a little bit easier when we then see the intermediates and the catalyst cancel. And then that will regenerate our V2O5 that we need to regenerate because that's our catalyst. Oxygen is of course a gas. So that then has enabled us to switch back to the +5 oxidation state. And if I was then to join those together to show the overall equation, I would be looking to cancel the V2O5 on both sides because it's going to appear on the left and the right. And then the V2O4 intermediate is also going to appear on both sides, leaving me with SO2 plus a half O2 makes SO3. And then we could write that alternatively as 2 SO2 plus O2 makes 2 SO3. So these will have to cancel. I don't really want to cross through them. I'll just put a little cross there instead. So we'll get rid of those, and then we'll get rid of those, and then we will combine that together to give us SO2 gas plus half O2 gas makes SO3 gas. And that shows how it's involved in the contact process, and that also shows how it's behaving as a catalyst, because we've been able to show that it will cancel from both sides to leave us with our overall equation. So 7 marks feels like a lot, but actually breaking it down, that's a fairly straightforward question when you know how. Obviously, if you don't know the definitions, that's going to be quite a hard question, and if you don't know the equations, that's going to be a hard question. But they are very common things that get asked about transition metal chemistry in lots of different exam questions, so you will get familiar with the equations and the definitions for this, and hopefully once that has become familiar, you will agree that that is quite a nice 7 mark question. Any questions at all, guys, as always, please just let me know. If anybody's got any similar questions you want me to have a look at, or recommendations, as always, please do get in touch. I hope you have a really lovely start to your week, and I'll see you soon. Take care.